My Astro-COLIBRI preferences, and well, we are interested in all kinds of transient that have the potential to emit very high energy, of course, like gravitational waves, GRBs, all sorts of flares, SGRs, novae, of course, AGNs, and tidal disruption events. So these events happen in the universe and they will emit their messengers. Either it's electromagnetic emission, gravitational waves, neutrinos, and these messengers will be detected by ground-based and space-based facilities. And these facilities will distribute their alert through brokers to follow-up instruments like radio telescopes and the IACTs. And some of these instruments are also detectors and follow-up instruments. I'll be talking about IACTs, so the last one down there. What do we have today as ICTs that are working? We have HES, which is my favorite. It's composed of 4 12-meter telescopes and a 28-meter telescope in the middle. We have MAGIC, and now we have LST on the same site in La Palma. We have Veritas in the United States, and FACT, which is also in La Palma. And I know that a lot of you know this, but when we talk about IACTs, we are talking about very high energy gamma rays. So it's tens of GeVs to 100 TeV. And the way of detection is important here. So what happens when a gamma ray enters the atmosphere? Luckily for us, it cannot penetrate the atmosphere, but it will interact and it will create secondary particles and cascades of particles that we call shower. These particles, they are faster than the speed of light in the atmosphere, so they have to decelerate and emit Cherenkov light. And this is what we see on our cameras. So these are the images of the Cherenkov light that we see. And a gamma ray looks like an ellipse. So once we detect the gamma ray, the ellipse, we can go back to the original properties of the primary gamma ray. For example, we can do a triangulation and go back to the direction, and we can also reduce the energy given the amount of light that's detected by the camera. Anyway, why is this important for us for this talk? Because now we want to follow transients, so we have to take into consideration the constraints of IACTs. What are the constraints of IACTs? First of all, visibility conditions. So this depends, of course, on our position on Earth. So if we are in the northern hemisphere, the southern hemisphere, we'll have different accessible skies. And the method of detection for IACTs puts a heavy constraint on zenith angle. So for most IACTs, I would say it's around 60 degrees, maybe 70 for some. So we cannot look farther than 70 degrees in zenith. And basically, this is what we will be looking at. In HES, I give always the example of HES because I'm in the HES collaboration. So we're in Namibia, and this is the part of the sky that's accessible for us at a given time. Of course, Earth rotates. We have observation conditions, it's an optical system, so of course we cannot observe when the sun is up. And also IACTs are fairly sensitive, so we cannot observe also when the moon is up, except when the phase is not is still early, or when the moon is not very high in altitude. So here's an example of gravitational wave. The blue region represents the visibility of our IACT in Namibia. So we can observe what's inside the blue region. This is accessible for us. The moon, our source shouldn't be very close to the moon, otherwise it will affect our data. So we cannot observe what's inside the orange region. So basically we can observe what's between the orange and the blue region. If it was full moon, or if the phase of the moon is larger than 30%, let's say, or 40%, depending on what configuration we use, we cannot observe. So we have several days per month where IACTs cannot observe. Okay, so this is an example of how to summarize everything that I just talked about. So we have a source, this is its altitude in the sky, and we have the altitude of the sun and the moon. Basically, when it's dark, this is when the sun is down, so we can observe, and when the moon is down. When the moon is up, if it's not very bright, we can observe, and the source can be observable when the altitude is more than 30 degrees. So basically, we can observe the source in here. Okay, so we have our transients, they distribute, we have the distribution of the alerts. Now we receive the alert, so I will tell you what happens on the side of IACTs. So I'll describe the transient follow-up system. From now on, everything will be describing what's inside that box. So let's start with, first of all, the TO alert system. This is the system that will decide if you want to observe this transient, if this transient is interesting for us or not. Okay, so we receive the alert from brokers or directly from facilities like we have with IceCube or Antares previously. And the first module is the alert receiving and archiving module. So this is where we store the alert, we archive it, and everything. The second module is an important one. This is where we define the science case of the alert, if it's interesting for us. There's, for example, Swift that sends a lot of slowing alerts that it's moving, so this is not important for us, so we filtered them out. And then once we receive the alert, we want to see what it is. Does it match one of the alerts that we are interested in? SGR, FRBs, neutrino, what is it? And then we have to prioritize our alerts. Why? Because we will not have two alerts at the same time, but like we would be observing an alert and another one arrives. So which one would we prioritize? So here's a small example. We have light GRB, Swift GRB, a neutrino gold event, flaring star, GBM GRB, SGR, binary neutron star, and binary black hole events, and FRB. So for me in HAS, this is how the priority is. So large GRBs, first of all, because they have the most potential of having very high energy emission. Binary neutron star mergers, because, well, they are interesting and we want to observe gamma rays from them. And then the rest of the order. Of course, this can change from collaboration to another. Okay, the third module is alert processing. So this is where basically the calculation is done to see if the alert passes our cuts, if it's visible for us, and if there's something special that we need to do for this alert. So basically we have cut evaluations. For example, we want to observe a GRB, but we don't want to observe it if the localization region is too large, so we can put a cut on other localization regions. We don't want to observe it, it's a known source, we want a new source, it has to be a new source. For example, we can put a cut on that. For SGRs, we can put a cut on the number of counts, so on the brightness of the event. FRBs on the DM, for example, because the DM can be an indication, an upper limit on the distance. So we don't want it to be very far, because if it's very far, we'll have a lot of EBL effects, and the signal will be very attenuated. And so on. So these are the basic cut evaluation, which are in the first part of this module. The second part is some custom processing. Some alerts need processing, special processing, for example, flaring stars. So we receive an alert of a flaring star, but we have to do our own calculation, if our own assessment, if this is matched to the known source or if it's a new source. So we do it inside this custom processing module. Then we have a special case where the alert is not well localized, where the transient is not well localized, like for gravitational waves, and we have to do some more computations, which I will explain in the next slide. And this goes into this module. And in the end, we have the feasibility computation. So, okay, the alert is good enough for us, it's interesting, but is it visible for us? So this is where we have to compute the visibility to see from when it's observable, and if it's observable within the time delays that we have, the maximum time delays that we allow. So let's talk a bit about localizations of transients. So GRB from SwiftBud, for example, or LAT or an FRB will be relatively well localized. So the localization error will be within the error region, within the field of view of an IACT. So it's just pointing the telescope towards this position.
But there are some events like gravitational wave events and GBM alerts and potentially neutrinos also that are poorly localized. So they have very large uncertainty in the sky, and they need a special treatment. Fortunately for us, gravitational wave and GBM alerts provide us with localization maps. So they look like that in the sky. So this is one of the best localized events. So this is the famous 170817 binary nucleus merger. And it was detected by LIGO, Virgo, and Fermi GBM detected the GRB. And the final localization region is 30 degrees in the sky, 30 square degrees. In comparison, the moon is 0.5 square degrees, so this is a huge area in the sky that we'll have to scan in order to find our transient, or in order to search for our transient. So we apply special methods. I will introduce them briefly for you. For these methods, what do we take? What are the ingredients that we take into consideration? First of all, the localization map that is provided. So it's a map that looks like this. So for each pixel, there's 4 layers. One that tell us the probability of finding the event, a 2D probability of finding the event in this region in the sky. And then there's 3 layers that give us information on the distance. And also we have to take the visibility and observation constraint that we talked about before. When we do that, okay, so we have these ingredients that we have to take into consideration. So what happens? We have the gravitational wave map. We bin the map. We change the binning of the map in order to have large pixels like that are around the same field of view of the IACT or a bit smaller. And we create a fake coordinate grid that will follow the map in the sky while Earth is moving. So we create this coordinate grid, as you can see here, and then we want to assess at the given time, which one of these positions is the best to observe. So we draw circles which represent the IACT field of view, and we integrate the probability inside these circles. And then we choose the highest probability to observe at this given time, which is red here. And we observe it, we remove it from the map, we mask these pixels, and then we do again for the next window until the night ends or until we cover the whole gravitational wave map. Okay, so this is taking into consideration the 2D probability that's provided by LIGO and Virgo and GBM. But if we take the 170817 example, it was a binary Newton star that's localized at, that has a distance of 40 megaparsec. These are, and this was one of the first gravitational wave maps. This is the 90% localization contours that was sent at the day of detection. And the yellow dots are the galaxies between us and 100 megaparsec. So as you can see, they seem homogeneous a bit, but if we zoom in between 20 and 60 megaparsec, we see that it's less and less homogeneous. And if we are at the distance of the event, we are left with just a few galaxies. So normally, I don't want to observe here. I don't want to observe empty regions. I want to concentrate my observations on regions where there are galaxies. So for that, I have another method, which is taking the probability provided by the gravitational wave interferometer and assigning for each one of these galaxies a probability, taking into consideration what I already have. So I assign for the galaxies that are around the region of the binary Newton star merger a probability, and then I do what I did before. I then assess inside each one of my circles, this time the 3D probability, so the probability of the galaxy which take into consideration the distance, and the 2D probability provided by LIGO and Virgo for one window, and then I do this for the next and next window. Okay, so this is a special case of alert processing that needs to be integrated into our IACT transient follow-up systems. So the second thing, the last thing to do is to assess the visibility. If it's visible right now, or if I have to schedule observation for the night, that for the upcoming night. So basically this module decides if I observe it promptly right away, if the telescope will move automatically, or if I have to put the positions that I want to observe into the schedule for the night, and then there's the distribution of the alerts for the experts on call, for the observers that are in Namibia or somewhere else, and writing the results and computing these summaries and everything. So let me show you also a concrete example about gravitational waves. So this is the timeline of the alert inside our TO alert system. This is the different tests that an alert will go through. So first of all, we decide, is it a CBC or a burst? If it's a CBC, so is it likely astrophysical? If it's not, we don't want to observe it. It's not interesting for us. If yes, we want to see what it is. Is it a BBA, a binary black hole merger, or a merger that includes a neutron star? Of course, mergers including a neutron star are much more interesting for us, and we have looser cuts for them. And then we have to select the algorithm. So which method to use from these two methods that I presented to you, a 2D or a 3D method? How do we choose the algorithm? Is that we look first of all at the distance of the event. If the event is close enough, we know that our galaxy catalogs are complete at close distances and we can use them. But if the event is very distant, we don't want to use galaxy catalogs because they are incomplete at very high distances. Also, like if the event is around the galactic plane, we know that the galaxy catalogs are not complete around the galactic plane. There's a gap because we can't see. Okay, and then we see the delay, we do our scheduling, we assess which positions are the most interesting for us to observe, and then we will see, is it visible now? If yes, then the telescopes will automatically to observe. If not, we will compute a schedule for the night. So if it's a binary black hole merger, we want to observe, we want to cover at least 50% of the localization region. If it's not, if it's a neutron star merger, we can allow for more flexibility, and as much as we have 10% of the coverage, we want to observe it because it's more like exploratory search. And yep, and we schedule our observations for the night. Okay, now I will show you the output, what comes out of this of these four models. So what do we distribute for the experts and the observers? First of all, we give them plots of visibility, as you can see here. So the visibility of each position during the night. Of course, a schedule, which anyway will be automatically integrated into the scheduler, and some visual aids. This here is just an assessment of the speed of the transient system. So everything I showed you requires a lot of calculation and computations. So we wanted to assess how fast can we be on target if we received an interesting alert. And we can see that it's around 35 seconds here. You will ask me about why there's two groups in our histogram. Well, this depends on the resolution of the map that we receive. So if the map has a very, very high resolution, it will take more time to read. So this will take 20 seconds more, and then it will take around 50 seconds to do this entire timeline. And plus we can add less than 1 minute for the telescopes to slew, so we can say confidently that we will be on target in less than 2 minutes for any alert, and in less than 1 minute for most alerts. Okay, so for the rest of the transient follow-up system, there are two things that I didn't talk about yet, but I will talk about them briefly. First of all is the data acquisition and observation schedule. So it's like the system, the interface between the TO alert system and the telescope. So it's composed of 3 modules. First of all, the dynamic scheduling. It's okay, so we received an alert, we want to observe it, but how do we say to the telescope that we want to observe it? First of all, we have to see, like, is this the position that we are already observing right now, or is it a new position? Do we need to extend the run duration or not? So this is done here. And then we have the center of control, which is literally the interface between the telescope and the system, which will send the new parameters to the telescope and we receive the new run parameters from the telescope. And then we have the data acquisition, like where the data will be stored and the event will be built. Then we have the real-time analysis, which is very important for us because this is a preliminary analysis done on site while we are observing. And I will not go through the analysis of VHE data, but basically this is important for us because these RTA, we call it real-time analysis results. If we have a GRB and or a gravitational wave, for example, and we are observing, and we don't know where the position, the real position of the event is, so if we detect it on the RTA, we know that it's here, and we'll concentrate all our observation on this position. We will not continue our scan. Plus, if we're observing, for example, a GRB, and we can, with our RTA results, if we have a detection, a preliminary detection, we can trigger other facilities. So we can send alerts manually to other facilities to tell them, hey, we detected an interesting GRB at very high energies, observe this, so we'll be able to accumulate data on it. Okay, I will show you two examples. It's like an outcome of what we already did. So this is the binary black hole merger, 1907-28, and it's a real simulation about how things go when we observe transient events. So the regions in yellow are the region on Earth that where the sun is up. So basically, we are in Namibia. We are somewhere here. So when we are in the yellow region, we cannot turn on our telescopes. The brown region is where the moon is up. So if the moon is sorry, so if the moon is up, we also cannot observe. And well, this is the gravitational wave map that is sent to us. The green circle is just a neutrino candidate event that also occurred at the same time. And the red line is the visibility of Hess, and as the gravitational wave enters the Hess visibility region, you can see that we start observing, the most interesting regions first, so the highest probability regions first, then we cover the rest of the map. So this is how things happen. I'll give you another example of the famous 1708-17. So this is very important for us. Why? Because, okay, so we got the alert. Our transient system told us where to observe. At the time, we didn't know where the counterpart was. So we were the first ground-based facility to start to observe this event. And our scheduler told us to observe this one here, then this one, then this one. As you can see, we started observing 5.3 hours later, then a half an hour later we observed the second position, then half an hour later we observed the third position. Then the moon rised and we stopped our observations. 5 hours later, so 11 hours after the reception of the alert, the counterpart was detected, and we discovered that actually the counterpart was in our first position. So we basically observed the counterpart. We believed our algorithm, and our algorithm told us this is the best region to observe, and actually it was we observed the counterpart, it was inside this region. And okay, I'm done. I leave you with the summary of the transient system of Hess. And if you want to take a deeper look, the slides are on Indico.